Let me say hello and welcome to our next VELOVirtual. Today, VELOVirtual, just to give you a little bit of background, is Velo3D's application deep dive. So this is where we look into the details around different applications or different parts that leverage the latest in additive manufacturing technologies. Today's going to be a little bit different though, and I'm going to explain that to you in a second. I want to draw your attention to this part over here on the slide. Parts like this part. So this is IMI CCI's high pressure flow control element. These parts take full advantage of AM, everything that you'd expect. They've got complex geometries, they've got lightweight designs, and they're extremely strong. And at IMI CCI, parts like this have been at the center of entirely new business units designed to find solutions for customers in the flow control area. But we're not going to talk about that today. We're not going to go into the design of the part. It's an amazing part. You can learn more about it if you'd like. Today, we're going to talk about what happens after you prove the concept. After you've got this part, it's fully designed, everything's ready to go. What do you do then? Like oil and gas or nuclear power, a significant challenge is qualifying AM technology and then competing with the volumes of data present for conventional manufacturing. These industries rely on decades of material development, and the transition to AM requires a careful consideration, in some cases, new standards, and then also you're going to need a scaled global supply chain. So how do you resolve that? Let me say it's my honor to introduce our speakers today. Steve Freitas is the Director of New Product Development at IMI CCI. Steve has over 25 years of experience in the design, selection, and application of high pressure and high temperature valves in fossil power plants and oil and gas facilities. His R&D team has over 10 years of experience in development and installation of AM parts at CCI, so specifically additive parts. The R&D team has developed several new valve designs using AM. They've worked with energy market customers all over the globe to validate these components for their applications, and they've installed hundreds of parts in applications with pressures up to 4,000 PSI and temperatures up to 1,100 Fahrenheit. So lots of real-world experience with additive parts. And then, of course, we also have Zach Walton today with us. Zach is our Director of Technical Business Development at Velo3D. Before joining Velo3D, Zach worked at multiple positions at Halliburton Energy Services, ranging from R&D engineer to product manager. He holds a BS and an MS in mechanical engineering from Texas A&M and has over 70 granted patents. So a great audience for you today. And Steve, I'm going to turn over to you.
All right, thank you, Michael. I'll tell you a little bit about IMI CCI and the CCI valve design. So IMI CCI provides specialized control valve designs that improve the reliability and efficiency of fossil, nuclear, and oil and gas facilities. The IMI design, drag design controls fluid velocities within the valve and prevents problems with erosion, noise, and vibration. And the heart of the design is the special flow control element, which has tortuous flow passages, which break up the pressure drop and reduce velocity as fluid passes through the valve. The way we manufacture these parts is we take two-dimensional plates and we create two-dimensional flow paths. The picture on the left shows a flow path where the flow path zigzags back and forth in the horizontal plane. The picture below shows how we take a stack of plates and make flow paths zigzag up and down in sort of a sandwich arrangement. These discs are brazed, unitized into a single assembly, and the drag designs are engineered for each application. We have over 10,000 legacy designs in our database, and materials include 316, 410, Inconel 718, and tungsten carbide. We make these parts in a huge range of sizes, from parts you can hold in your hand, like this little disc stack right here, to parts that are 6-7 feet tall, which go inside condenser dump devices, like the pictures on the right. So huge range of sizes, engineered to order for energy customers around the world. About 10 years ago, we began experimenting with laser powder bed fusion for making these parts. We started this in 2008, and we started shipping parts in 2009. Our goal at that time was to improve flow control accuracy of the very, very small disc stacks, like the kinds you can hold in your hand, because these have a critical impact on the process controls inside some power plants. Our process was pretty simple: design a part, build a part, see what came out, flow test it, and then see what happened. And at that time, we had a lot of challenges. We could not build our legacy designs without re-engineering. Our legacy designs use flat overhangs, like the picture in the top right. When you try to build parts in additive with flat overhangs, it's an enormous challenge, and you get these kind of bubbly dropout features due to the unsupported upper surface. We really lacked knowledge on the process limitations of AM at that time. And the parts, as a result, did not always meet our expectations for performance or cost. So it was a real hit or miss, onesie twosie approach to development and shipping parts and customers. We made it work, but it wasn't satisfactory. And then in 2017, we conducted a complete re-engineering of the parts around the limitations and optimization for laser powder bed fusion. It was a sort of a DFAM, designed for additive manufacturing approach. And this was really a huge change for us, which improved our performance, cost, and lead time. It showed us how to make parts that were consistent, and really has been a big change to our business. Since then, we've shipped over 500 parts and are starting to phase out our legacy processes for many sizes of valves. For bigger size valves, we started again from scratch, and this picture on the right shows two disc stacks. Both are made from Inconel 718. These disc stacks are used in power plants, which operate up to 1100 degrees Fahrenheit or 600 degrees Celsius. Typical sizes, this range of products is from 4-inch to 20-inch. The two on the right are 5-inch nominal disc stacks. Both are designed for the same performance envelope and the same dimensions. But with AM and the power of AM and design for AM approach that we created, we're able to reduce the volume of the part on the right, the AM part, by 25%. This really lets us use AM in a much broader range of applications than we could in the past. We validated the design through CFD, flow testing, FEA, and load testing. And the reduction in AM part volume and subsequently cost, and the massive lead time improvements we can get with AM, facilitated a changeover of our legacy parts to AM technology across the board throughout the business. We have many of these parts in the field right now. We're currently limited to a 10-inch part size. We'd like to make this much larger in the future. And in fact, just this week, we're talking about making a 14-inch size disc stack, which is an enormous piece of metal in AM. And the way we validate the design is actually quite simple. We are a manufacturer of valves that control flow. So the picture on the left shows our technician loading up a disc stack in a flow test configuration where we blow air through the valve and measure its flow performance. And the picture on the right shows us taking an AM disc stack, putting it between a hydraulic press, loading it up and measuring deflection. We want to make sure with AM that the new part designs have equal or superior performance in terms of both flow and structural integrity, so we can exchange legacy designs for AM parts and give our customers the benefit of AM too. But with AM, we can do much more than make cylindrical disc stacks. We can take advantage of the full capabilities to make things we couldn't make before. We can make parts that are geometrically complex, but also strong and lightweight. So this is an example of one of these parts. This is a drag element, which is used inside a ball valve. The drag element is the elliptical piece on the left. It's about 18 inches across, 8 inches tall, 8 inches deep. It's a really large AM part. It was manufactured with laser powder bed fusion. It was integrated into the valve assembly on the right. So that picture shows the drag element combined with a traditional drilled hole element installed inside a 24-inch 900 class ball valve. So we can now do things with valve performance we couldn't do before. We can make valves which have had sort of traditional legacy performance characteristics perform much better, give our customers more value, and help their plants run more reliably and efficiently. We also recognize that with AM, we're no longer restricted to just making the disc stack design that we make in our drag valves. This has been a transformative idea at IMI CCI. We've built a new business unit around helping customers find flow control solutions with AM technology. The picture here shows two different AM parts. The one on the left is a typical cage or disc stack design, which might go into a CCI valve or even a competitor's valve as a retrofit, where you take out the legacy part and you put in a new part, fits in the same envelope, but has much higher flow performance characteristics, much better reliability. And the part on the right is quite special. We can actually have a valve or elbow someplace and install multi-stage compact flow control elements inside a valve or inside a flow elbow someplace and control velocity and prevent damage and erosion in applications we haven't pursued before. So that's been a huge change for us. But with AM comes some new challenges too. So one of the outstanding challenges is qualifying AM technology for critical applications. in the oil and gas and nuclear power industries. These industries, as Mike pointed out, rely upon decades of material development to ensure the integrity of their facilities, and they are in some cases prohibited from adopting new material forms without changes in their underlying codes and standards. There have been some new standards for AM material qualification published in the past few years, and we're working with our suppliers to qualify our parts to these standards. The transition to AM requires careful discussions with our customers about the application risk and the qualification options, as this sort of a matrix of technology and qualification matures year by year. So that's very exciting. One of the programs we did recently with great support from Velo3D and in partnership with one of our oil and gas customers was to make an accelerated program to see how we would apply AM technology in an oil and gas facility. And so we work with our customer to identify a candidate valve design, which in this case was a choke valve. We had an accelerated process development. We looked at both the valve design characteristics, how to specify the parts for AM, what test coupons to build, how to measure those test coupons. So we had a very fast, rapid focus on those areas to generate a process specification. The build and its characteristics were optimized for the customer field conditions, because with AM, we can sort of customize for each application. And we've followed the documents or requirements of a standard called API 20S, which is a recently published oil and gas specification, which defines how to validate and control AM parts. And this provides a real roadmap for us for how to establish a scalable supply chain around the world, how to deploy consistent parts in different sites with reliable metallurgy for our most critical customers. And these parts are currently under field trials, and we're really hoping to have some good results on this. And now I'll turn over to Zach to talk about the Velo3D technology.
Yep, thank you, Steve. So like you saw in Steve's section of the presentation, there's a lot of kind of synergies we saw between Velo3D and what IMI has been doing over the last several years. So our plan is to go through our technology as well as in detail of how we qualify the parts he showed in the previous section. So Velo3D was founded in 2014. As of close to the end of last year, we are a publicly traded company on the New York Stock Exchange. And what we've brought to market is a revolutionary new end-to-end metal AM solution. The goal of the solution is to deliver complex, high-value metal parts without the design or quality compromise that have been seen with legacy processes or legacy metal AM. We do have service and support worldwide, so we are a worldwide company, but the technology is designed and built here in the United States. So some of the companies that we work with, you can see listed on the screen, but the real intent here is to show across different industries, a lot of these supply chain and kind of design consideration challenges are the same across different industries. They might just have to adhere to different specifications or be called have different challenges. But between aviation, space, energy, and defense, a lot of what we're going to talk about today, including what we've done with IMI, translates fairly well. So a lot of the parts that we find our technology mostly used for are static and rotational parts that are optimized to control flow of fluids and or the transfer of heat. And our main goal is to provide these types of parts to our customers without basically getting the exact part they want, without needing to compromise things like quality and geometry, which we'll go through in a few of the next sections. So what is the Velo end-to-end metal AM solution? Our end-to-end solution consists of three components. So Flow is our proprietary preprint software that allows CAD to be loaded into the software, a build to be set up, and create an instruction set that the printer, so the next section, the Sapphire printers can then execute these instruction sets. And the Assured Quality Validation software is the third component that takes a lot of the data and information before, during, and after the build to provide information on the health of the actual printer itself, as well as tremendous amount of data and information on the end part quality. So at the heart of it, the manufacturing technology is laser powder bed fusion, which essentially you can see through these graphics. We are laying down a finite layer of metal powder and then lasing that instruction set for that layer, lowering the piston, again laying powder, and then continuing this process until we have a fully complete part at the end of the print. Now, it's important to see one of the benefits, one of the first benefits of what we've done with our end-to-end solution, which is to understand that you have to understand supports in metal AM, which are actually anchors And the best analogy is shown through these images, where on the bottom left, you have a desired outcome, like the flow channel that Steve went through on some of their valves. What happens in conventional AM, if you don't anchor or support that area, you have warping of the metal. In traditional systems, something's going to give, either the part, like you would see in this example, or the recoder on the printer itself, or both in some cases. And so to adhere to that, you either have to change your design, like Steve mentioned they had done in 2017, or you have to heavily support these internal channels, which is very cumbersome in terms of post-processing and removing those supports afterwards, since they're made of the same material that the part is. What we've done here at Velo3D, and one of the first benefits of our end-to-end solution, is focusing on printing the part that you actually want, whether it's a legacy or a new design, and working towards not having to defam or change that part or add anchors. So one of the, this leads into our first kind of discussion on one of the parts of the end-to-end solution, which is the Flow preprint software. So Flow, it intelligently identifies different features because we are working with the native CAD file. Each feature is automatically assigned a pre-developed recipe. And these recipes are aimed at overcoming feature-specific failure mechanisms. And there's a library of dozen recipes that we're continuously growing and have been growing over the last several years. And the software is built with flexibility to define and identify some of these new features. So going into even more detail, kind of drilling down on the Flow preprint software, using the example of the cages or choke valves that we printed with IMI here recently, you break it apart into two sections. One is the Flow build preparation. So in this case, you would import the CAD file, you would orient and support the part as needed, and then apply any amount of sub-processes. So you can see this visualization on the top section. On the left is the Flow build preparation software, where we've imported the CAD, we've supported the parts, and then on the right image, we've applied a sub-process by selecting all the surfaces of the channels and doing a sub-process that is intended for these small type of channels that allows for more consistent performance once printed. You're also then able to populate the build plate. So you can see the blue is the first set of information that was put in there, first set of CAD, and we're able to translate that exact geometry to the right on the green section. From there, we move into our second phase, which is the Flow process review. So we've now sliced the part into 2D sections, which is essentially generating the laser instructions. And then this print file that's generated, this is what contains the locked-in print instructions or laser instructions that can be printed on any of the Velo Sapphire printers, and also allows for review of the prepared print file, which you can see on the bottom right section. So to understand where the process is stable, there are sets of design rules. So in this case, working with Steve and his team, we needed to understand what where the stable region was for different closures. So how thick the actual top thickness of the channels are, as well as at what angle they were positioned in. And so on the bottom right, you can also see one of these similar type cages kind of being built to show, this kind of design geometry. The next up is the Sapphire family of printers. So if you look at the bottom right, the first identification is the size of what you can actually print, or the build volume of the printer. So for Sapphire, it contains a 315 millimeter diameter by 400 millimeter tall build platform. The Sapphire 1MZ is the exact same construction. It just has the ability to print taller, up to a 1 full meter. And then the Sapphire XC is our newest development. That's intended for larger parts or more of the same parts, hence the XC for extra capacity. And it's a 600 millimeter diameter platform with 550 millimeters tall. The lasers on the system, so Sapphire is equipped with 2 1 kilowatt lasers, and the Sapphire XC is 8 1 kilowatt lasers, and both systems have in-situ laser alignment. The inert environment is argon, and the process layer thickness is a standard 50 microns. It is equipped with one-click calibrations, which we'll get into in the next section, and is equipped with multiple metrology and sensor capabilities to be able to document essential variables and data during the print. In terms of the production-ready material, on the top section are the materials that are qualified for our system. So what that means is we have mechanical properties vetted and understood that we can provide, as well as all the parts that you've seen on the previous slides. The process recipes have been created and qualified for those materials. On the bottom, you see the coming soon alloys. And then the estimation that we typically give is about 3 months to do the qualification, which is important to understand, and why we call it production ready material processes is we provide the mechanical understanding, as well as make sure that those generalized recipes are transferred, again, to print all the parts that you've seen in the previous slides. The last part is the assured quality software. So this is broken down into multiple sections. One is factory monitoring. So people that own our printers or own a fleet of printers can see a real-time kind of fleet tracking, can see all the printers and drill into live build process progress monitoring on any of the prints going on for those printers. The tool health ability to have one-click system calibrations that can be checked before every single build or at the cadence of whatever a specification or a provider and end user have come to terms with. And then the in-process monitoring, so things like optics health, powder bed quality, and the build chamber environment that's being monitored throughout the entirety of the build. And then build reporting is one of the big keys that we'll talk about when we go through the API 20S qualification that we work with IMI on, where all of this information is put at the end of the build into a PDF, which we call a build report, that has all sorts of information on the build itself, as well as the tool and build data documentation. So the other advantage beyond the geometry that can be printed and the reduction in supports and having greater design freedom, putting all these pieces together, specifically the locked in instruction set that's created by Flow and the ability for the systems to be, the calibration to be checked before every single build, it's really enabled what we term the golden print file, which really allows for a flexible supply chain. And what this means is that a single print file can be created and can be printed on any Velo3D printer of the same material at any location, no matter who's operating it, and expect to get the exact same end part. So our global contract manufacturing network, we have a handful of contract manufacturers in the United States and around the world, and are continuing to grow this manufacturing network to provide that type of global supply chain flexibility. So focusing on the oil and gas cages that Steve brought up at the end of his section, what we wanted to walk through is how we use the end-to-end solution to really qualify these type of products. And again, it's the same for most industries. You're going to focus on material qualification, the actual system or process qualification, in this case is the Sapphire, and the actual part qualification. So moving to the next slide, the material qualification, because Steve and his team had such a history with laser powder bed fusion, there wasn't necessarily a database of materials that needed to be understood. They understood kind of laser powder bed fusion and what was capable and what to expect from a material process. But the rest of the industry, the rest of the world is not always there to that extent or have that history. And so there's a lot of things like MMPDS for aerospace and defense or NACE type qualification for oil and gas that are founded in kind of statistics of mechanical properties to provide people the comfort of using this type of process or these types of processes to design their parts and have be comfortable in the material. And so because of, again, our integrated push button printer calibration and our one print file for all printers globally, we're able to go work with these industry kind of specifications and be able to lower the barrier or increase the comfort of using these type of materials, or in the case with Steve and his team, be able to push into even more aggressive applications such as NACE type environments. The next step was a Sapphire qualification. So this was the first production valve produced on Velo3D technology. Like Steve mentioned, we applied the standardization of API 20S, which specifies how to set up the builds, what testing to do, and what documentation needs to be provided to meet the API 20S spec. And then Steve and his team, based on their history, provided the success criteria. So we did the first article build in accordance to API 20S in AMSL level 3, which is the highest criticality. The API 20S essential variables that needed to be documented were automatically part of the build report. So those same essential variables are the things that we consider as important to monitor during the build and supply in the build report. And the flow test demonstrated the consistency of the generalized process provided by Flow, where you can see on the chart on the bottom, the first ever valve printed on our technology, meeting the flow characteristics needed for this application. So now that the Sapphire was qualified, the next part was the actual part qualification. And so moving on into the production build that's called out by API 20S, we were able to produce the parts. And like Steve mentioned, these valves are in field operation for a major oil and gas operator. So moving again into the second phase of being able to print across a large network and increase the supply chain flexibility, we have two examples here. One is using conventional AM, where you're taking a CAD, creating an STL, a build file, and then depending on the technology, there's different items that can pop up, whether you're wanting to print again in the next week or printing a year or two from now. that can sometimes complicate being able to have a global supply chain or kind of digital inventory approach. Essentially, the way I look at it is being able to create a bill of material and locking in the as printed model, saying this is what I would print a year or 20 years from now. On the bottom, kind of simply drawn out is what the end-to-end solution is capable of, where we can take the CAD geometry, create a Velo build file, slice the file, create a Velo print file. And because that's a locked instruction set, and because of the way our printers calibrations work, we have this golden print file that can print on any Sapphire anywhere in the world of the same material. And so what we've been able to do, kind of adding further context to what Steve has gone over, is you see the 3-inch choke valve that he discussed for an oil and gas production facility. We've been able to, or IMI has been able to confidently move across our network of contract manufacturers and print things like this 12-inch gas letdown valve for an offshore facility, as well as this 10-inch boiler feed pump valve for supercritical power plants, and have the confidence that the end part quality and the design is intact once complete. And then in terms of the 3-inch choke valve, you can see now that that part has been qualified in-house. Now that part's been qualified either on someone's in-house printer or an external printer, in this case, working with IMI. After qualifying other vendors, they now have the confidence, whether it's 2 weeks from now or 2 years from now, to print that same print file at any of these suppliers in the future. And I'll pass it back over to Steve for the conclusion.
Thank you. So in the beginning of our journey at IMI CCI, we were happy just to get one, cool piece of metal printed was a cool thing to do. But now that we're scaling up the business around the world, it's very important to us. We recognize the value of having an end-to-end solution which controls quality and consistency. So we find the Velo approach to be very attractive in that regard. The flow print preparation software leverages past years of laser powder bed fusion experience. We don't have to reinvent the wheel each time. It uses the qualified build recipes with print file instructions that are locked. We don't have to worry about if things are changing behind the scenes. It maintains IP for the print instruction file, which again is increasingly important as we deploy around the world. Does not require a process development engineer to reevaluate each build every single time. Reduces the variability often seen from manufacturer to manufacturer. So this was a big concern for us. If someone buys a different machine or we go to a different supplier, how do we manage all that as a valve part supplier? And then the Assure system provides the in-part quality, the monitors and process of and reports on calibration and essential process variables, and provides validation that the flow print file will be executed consistently from machine to machine globally. And then the benefits to us is this gives a more scalable supply chain for IMI CCI and Velo3D. And our customers are global. We have to give them global consistency in terms of quality and execution and material science. So that's very valuable to us. It paves the way for IMI CCI to qualify our AM parts for energy industry quality standards because it removes question marks around consistency. It gives us what we need to move forward. And the Velo3D technology can print our legacy designs without DFAM, designed for additive manufacturing. That's very attractive for us, given our huge library of reference parts. And we can print really large parts, up to 24-inch diameter with the Sapphire XC technology. So we're very excited about the work that's going on here in the way forward. Thank you.
All right, that was really awesome. And I've got a great question to get us kicked off here. Lynn brings in the perfect question. So if you've been to a trade show, you've seen, we're lousy with great looking parts. And Lynn, I think you hit the nail on the head here. The benefits of AM to resolve supply chain issues are pretty clear. Why isn't the scale of AM used in supply chains 10 times, 100 times what it is? And I think that's a great place to start, and we'll kick it off from there.
Well, I'll speak from our experience. So I remember when I first read about the AM, I thought, I don't want to go there. It sounds like a mystery. So people that haven't looked at it don't understand the power of it, I think, and what's available with it. So there is always a certain inertia in the organization, I think, to make these kinds of changes. Because when you make a change in metallurgy, a lot of questions come up, and it does require a very confident look at both the application risk and how you're going to manage it. But again, our experience has been very good. We think it's very much worth the journey and encourage people to talk to suppliers, talk to their end customers, and have those discussions.
I think from our side, the benefit of what we've developed from the end-to-end solution has really been to, like Steve said, you're changing a manufacturing process, and there's sometimes a list of things that you have to consider. And if you're having to change the design, if you're not able to have confidence in the same end part across different vendors, just changing the manufacturing process and adding those other variables can be sometimes hard to swallow across the manufacturing quality, what have you, in the engineering organization. We feel like we've lowered a lot of those barriers and made it to where you are looking at, like Steve said, focusing on the mechanicals. Is the microstructure okay, and then being able to confidently kind of scale metal AM.
So, I mean, kind of connected to that original question, do you expect over the near term you're going to see a spike in AM applications, given this technology exists now to fill in some of these gaps?
I think we're just on the start of the transition. We've changed our disk stacks over to this because they're obvious. They were high number of process steps required. I think that there's another jump to be made when people start looking about the bigger picture of how parts are used, how they can integrate assemblies, take out process steps, which makes it safer, faster, and easier to make parts for customers. So I think we're just on the beginning of the journey.
Yeah, fantastic. There's another question in here from Amy. Amy asks, is NDT done on the AM parts in situ monitoring, or do you use only the flow and hydraulic press deflection test to qualify the parts?
Zach, you want to go first on maybe cover the your end?
Yeah, so typically, I mean, it's kind of defined by the designer of the part or the specification being used. So in the case of API 20S, each of those builds, they contained a set of mechanical samples that needed to be tested. And it also included some amount of NDT that was required to be performed. And even more so because we did it towards AMSL level 3, which is the highest category.
And then on our end, we have to look at each application a bit uniquely. So certainly for critical applications in oil and gas, there's a higher level of integrity required testing. So we look at each application, each industry, say what do our customers expect and how do we want to address those uncertainties? And then we generate a test specification accordingly. But it varies from simple to more complex. You just have to understand the application.
Excellent. There's a question for you, Steve, another one from Len. How do you find applying the requirements of API 20S? How are you providing assurance of its application? And do clients understand what it is and isn't?
There's a couple questions there. So I think the 20S was published past, I think this winter, I think it's still being promulgated. I think very few users in oil and gas or oil and gas customers are aware of it yet. I think it will grow in importance. I think you have to engage very closely with your suppliers because, as you can see from the presentation by Zach, there are things you want to monitor and watch, and you want to have a good partner for that process if you're ordering parts to 20S and AM.
Awesome. Zach, any color on that, or Steve covered it, I think?
No, I tend to agree with Steve. I think it's a conglomeration of what was required. A lot of these standards and specifications of all the technology that's available. And I think one of our benefits that we saw, to Steve's point, is working with us. Most of the stuff that need to be documented or understood, it's stuff that we're already monitoring and outputting in our build report, which should over time, things like that simplify the how to apply to API 20S.
Okay. A couple questions on the global supply chain that you mentioned earlier. How do the current global material availability or supply chain issues affect Velo3D's manufacturing timeframe? And has powder availability and or quality been affected by this? That's the first.
We haven't seen any quality or availability issues with the already kind of approved and qualified materials. Some of the newer materials we're looking at that aren't as well known in kind of metal AM, meaning only a handful of solution providers have looked into those alloys. Spinning that supply chain up and having that be a stable supply chain, I think, is the biggest thing we've seen, is mainly the newer, more exotic materials that people are starting to explore.
This one from Stefan here. To use a worldwide, the same print file sounds good, but then all machines must be in the same condition or calibration. But there are always some tolerances. How do you compensate for this?
Yeah, so there's quite a bit of detail on that question and things we probably need to cover in a completely different session. But the way we handle our calibrations, and then the way that the print file is not able to be changed, ensures that you're getting the same end part. It's things that we're doing in different industries right now through our CM network, and actually have some studies going on with Steve to in his company to prove that out even further. I think to go into the excruciating details of how those calibrations are done, I think we have a previous VELOVirtual, as well as we'll probably have a different session, to be honest, Mike, where we go through that in quite a bit more detail.
Yeah, it's a great question. If you want to know more about calibrations, we have a ton of content on it. It is definitely Absolutely. A differentiator for us, and we do take pride in that. Okay, so another one from Len. To scale the use of AM, how are you analyzing SKUs to find the ones where there is a good case to go with AM? And you kind of mentioned it a little bit before, Steve, some of your thought process around selecting parts.
So I had a lot of discussion in the past with some of our leadership here, and they would bring me parts which were made from bar, right? So a part you can make from bar and put on a turning operation, probably not a good case for AM. But if you're taking that part and you're adding a lot more features to it, a lot more multi-axis features, then you should be thinking about AM. So for me, the Distax was an obvious case because I had such a complex, rich geometry in the part. And so that was an obvious one to pursue for AM. But to me, that's, at least in my world, we kind of work in either parts made from bar and castings or the Distax. So that was, again, I was very fortunate I had an easy target to go after.
I think kind of to add to that, that's why we've even created this newer team. Mike hinted at that I'm now leading in terms of the technical business development. It's really an extension of what me and Steve have worked on for the last 2 years, which is understanding surface finish, understanding tolerancing, understanding the actual design intent, having a very technical engineering type discussion on these type of parts, any type of parts at a company, but more importantly, finding what those challenges are. And so like Steve said, if it's something that you can just turn down very simply, it might not lend itself. And as you get more and more complicated, add more and more processes and have, to be honest, even more and more pain in the supply chain, those are usually good candidates that start popping out.
Can I just add one more point to it too? So as Zach was talking, I was thinking, so if you have a part that's already a high alloy part, it's worth looking at. If there's a part that's not a high alloy part, but making it a high alloy part provides the opportunity to provide more benefits to your end customer, better performance, lighter weight, better reliability, then those should be looked at too. Because one for me of the powers of AM is it unlocks the ability to use high alloy parts in whole new configurations and fully leverage their capabilities that I couldn't do before because I was buying dumb pieces of bar and dumb plates. So that's a very attractive potential for me.
And even bringing that back to the supply chain, like a question from earlier, if some of those higher alloys are required, buying that plate and bar now is a bigger supply chain issue that I see than getting the powder, since you're using such little amount of the raw material to make the part in metal AM.
Yeah, it's a great point. Brandon asks, this is a great application for AM. Can you comment on any surface finishing processes that were used for internal channels of the Distax?
That's a very good question. So whenever you're looking at an AM part transition, you really have to, maybe before you do or as you do it, is stop and look inside the parts you make today and what is their real characteristics and what are their real process uncertainties. So the parts we make today are not perfectly smooth on the inside. So I took advantage of that because AM is different from polished metal. It's different from an as-rolled condition. It's not bad, it's just different. And I was able to benchmark that against what we did already and make the judgment that it was probably going to be okay. In addition, we validated that with flow testing. So you do want to, like I said, when you start the journey, you really start to look at your current parts and say, what do I really know about them or not know about them? Because there may be some opportunities for AM you haven't thought about before.
Yeah, I think that's a great analogy, because usually you're starting with a part or a design. And sometimes the surface finish requirement through history has been dictated by the manufacturing process instead of the need from the actual application. And I think AM, it opens up that sometimes uncomfortable, but to be honest, kind of fun from an engineering standpoint, understanding of digging in that. I know, my time at Halliburton, I was notorious for the one that always questioned why 125 surface finish was called out on everything. And sometimes it's a standard that calls that out. Sometimes it's the manufacturing process versus actually what you need to actually for the performance of the application.
And then there's another question. Doesn't AMSL3 require a test for each part?
So AMSL level 3 requires you either have to test a sacrificial part, or you can have prolongations. And in this case, we used prolongation. So I think we might have, when we showed the pictures to the right of the finished parts, what we didn't show is the same build was run for the first article as well as the production, which included hardness, impact samples, tensile samples, density samples that were all tested each phase of that.
Okay, excellent. So that is what I have for questions. Steve, I'd like to get some closing thoughts from you. I'll turn it over to you.
Oh, okay. So thanks everybody for the questions. I hope you enjoyed the presentation. And if you have any questions about how we've applied AM, I'd be glad to be available to help answer those. And I want to thank the team at Velo for their support on this session and on this project. Thank you.
Great. Zach?
Yeah, so to reiterate what Steve said, thanks everybody kind of for having us. And if there are questions, kind of the support that Steve's talking about, that is what our teams do. One of the big elements of how we support our customers, even people that don't plan to purchase a system, is looking at the applications, helping transition some of their parts that make a lot of sense in our system, into production.
So thank you all very much, and have a great rest of your week.
Thank you. Bye-bye.
Thanks.